Hello everybody, we are Harry, Jin, and Wani doing our CAS project, giving a pretty concise, thorough run through of the whole math unit you guys need to know for eAssessments that is going to come up. And our main purpose of this video is to inform you guys so that you guys don't have to go through a lot of pain when studying for e-assessment as we did. So we're here as a guide. We'll be making sets of videos for the 4 units that we have prepared, and we will also include optional things, but we'll clearly state this part of the unit is optional. So you guys can just listen to our videos. Now then we will look at the first unit, which is Unit 1, Numbers and Algebra. So the thing about this unit is that this first unit is rarely tested on the exam as its own, but these techniques will be used repeatedly throughout the calculations in more complex problems in the test. So think of this as just a quick review of the different terms and different methods. First, we will look at the different ratio, percentage, decimals, and fraction. This is a really concise and easy straightforward part, so I'll just look it over real quick. To wrap up this section, it's important to know how to switch quickly between the ratios, percentage, and decimals, as you can see here. If you have a ratio of 3 to 2, you can just write it as 3 over 2. For every 3 blue pants, I have 2 red ones. I have 3 over 2, or 1.5 times as many blue pants, and then I have as red ones. 3 over 2 can be converted into percentage by decimals using the calculator or using your knowledge of knowing the ratios. If the number is 3 to 2, it is same as 2 over 3. So as you can see, the bottom number goes to the denominator and number 3 goes to the numerator. If you want to concisely get percentage, you should also know that you have to multiply by 100% so that it actually gives you as a percent value. And this unit's pretty much straightforward because the only thing you do is conversion. And one thing you can keep in mind is that you can also go backwards by dividing 100 to get the decimals. So for instance, if I have 75%, this is not 75. I'll just show it clearly with the red pen. But instead, 75% is 100% multiplied by 0.75, and 0.75 is also 3 over 4, which can be written as 3 to 4. So this is pretty much you guys need to know. This is not a really difficult topic. You just have to know the difference between conversion and yeah, no, this is a pretty much easy skill that you can always use if the numbers are in percentage or ratio. You can just change it in the way you want so that you can understand the question more easily. Because sometimes when you solve math questions, it's better to see the numbers in different ways. So, for example, if they tell you that they have 75% of cats and 25% of dogs, it's easier to see what the question is asking for if you convert it into a fraction or ratio. You have 3 over 4 cats and 1 over 4 dogs. Yes, so this is how you can use this unit. Make sure, even though I say it might be straightforward or easy, these units it means that they're very fundamental. The concepts are easy, but they come out a lot frequently. So it doesn't mean you guys have to you guys can just go over this topic because it's easy. You guys have to make sure that you understand this unit completely, and yeah, you guys have to know how to convert these ratios into fractions, fractions to percentage, and find the specific ratio, which are these guys. So you have 1.5 more or something like that. Absolute values are the absolute value or modulus of a real number x, denoted in this notation here. You can simply think of it as changing minus to plus and leaving the plus as it is. So what I mean by this is, as you can see in the example, if you have minus 7, if you do an absolute value, that becomes plus 7, and if it's already a plus 7, that's just plus 7. Now, if you really want to understand the absolute value clearly, I will briefly explain the real meaning of absolute values. It's actually the distance from 0. Now, what I mean by this is just bringing back the example before. Let's just extend this a little more so that both sides are equally lengthed out. Yep. Let's say this part is 7 and this part is minus 7. What the absolute value is asking for is actually the distance value of how far the value is from the origin. So even though the value may be minus, the distance is just still 7 because that's minus 1, 2, 3, 4, 5, 6, 7. So this is the real meaning of absolute value. So if you understand it this way, it'd be better, easier for you to memorize. I mean, but everybody kind of have a sense on what absolute values are. So I'll just move on to how to solve for these terms. Now, the specific thing is these things, and these equations may look straightforward, but they become confusing because of the notation they use, like this bizarre way of expressing it. So if I were to just look over real quick, x absolute value, it just means that for any value of x, it will just become a positive x value if it was originally negative. And this thing is, this equation here is just another way of representing absolute value. You can just, give me a sec. You can just write it this way. And some people asks, is it okay if it's done the other way around? Um, the short answer is yes, it should not matter, but the long answer is no. The reason why the long answer is no is that if x is lower than 0 in this case, not equal to, lower than 0 in this case, it means that there's a negative value inside a root. And this results into I, a imaginative number that if once you square becomes minus 1. So it actually turns out the square value is not the absolute value. So you guys have to know that this is not same. So root x squared is not equal to x root over square. They are very different. So yes, these diagrams are clear, so I don't think I need to go over. One thing you have to understand that is when there's absolute values with inequality. Now, if I just move this guy, no, I'll just move this guy a little top for a sec. And if you see here, for instance, if the question comes out as an inequality like this, you guys have to make sure these two are not the same. They are not the same. There are different equations because absolute value notation states, as I said, is a distance. So you have to also consider the negative signs. What that means is that this absolute value, once you remove the absolute value sign, it will become like this. Because the distance value, the realistic value, has to be just smaller than 2. X itself has to be bigger than minus 2, but also smaller than 2. So you have to make sure you understand these type of inequalities because they are special and they might confuse you. So you have to understand that to remove the brackets of absolute value, you can simply put minus and plus on the both sides on left and right. Or you can just understand the fundamental concepts so you don't freak out looking at absolute values. Now we will look at law of exponents. For the law of exponents, there are 6 important systems you should understand. They can be seen in the table here. Yes. Multiplying two exponents with the same base, just add the exponents together. Dividing the two exponents with the same base is just subtracting the exponents. And raising an exponent to another exponent is just multiplying the exponents together. Now, it's easy to make a common mistake by raising the exponents to the power of that exponent instead of simply multiplying it. So what I mean by this is that exponents have a strict rule of their own kind. So if, as the question states, I have 2 to the power of 5 and 2 to the power of 2, it's a common mistake that is found that students tend to do 2 to the power of 10. But this, as I explained before, is utterly wrong. And it would rather just be 2 to the power of 7 because it's 2 to the power of 5 plus 2. So one mistake, you guys, in order to not forget this, is that you guys have to understand that exponents work differently. They have their own system, like log and roots. They have their own way of addition and subtraction. So you guys have to understand what specific rules they have and understand them clearly. So if I give another example, this as it's in the bracket, they will become multiplication. So this will become 2 to the power of 14. Um, if you guys really want to learn how to not make a mistake here, is you guys have to just practice on and on until you finally get the concept inside your brain. One thing special is these two here, right here. These two guys are very special, and I'll explain what they mean. First of all, any number to the power of 0, so 2 to the power of 0, is always 1. Now, there's a specific mathematical reason for these type of numbers, but since we're just studying for the exam and we don't really need to completely understand the system, the question will not ask you why this happens. So I'll just go over it, but you guys can just remember, if anything is to the power of 0, it's always 1. Now, next we have that notation of minus to the power of minus. And as the equation states, the number becomes the denominator. This is just simply because to the power rule where a to the minus 1 is a over 1. Oh, that looks like a 9. Ew. Yes, a to the power of 1. So you can just simply represent this easily. And the only takeaway you should take is that if there is a negative value, it means that it's below the fraction, and it becomes the power of the denominator. We have this guy here, which is called the equate indices, which means that if we have the same base, I'll use 2 because 2 is the most commonly used base number. 2 to the power x is 2 to the power of 4. It just simply means x equals 4. So exponents have their own rule and they play by themselves. Therefore, when you're trying to solve exponential equations for x, it's helpful to try to reduce to having the same base number. So in this case, the same number 2, because they are easy to understand and represent, and it makes things much more easier. In order to get this result, however, you may have to change the exponents by simplifying it. So I'll tell you what I mean by that. Oh, we don't have an example here, then I'll just show you by myself. Um, if I have a number, I'll just think of an example question right now. If we have this type of question, we all know 9 is 3 multiplied by 3. I'll write that again. We all know 9 is 3 multiplied by 3, which is 3 to the power of 2. So it'd be better to represent 9 in terms of 3. It'd be better to represent 9 in terms of 3 because we want to have the same base as we have x as an exponent. So if I change it, it will become 3, 2, because this is 9, over 4 to the power of 4. So it will become 3 to the power of x is 3 to the power of 8. Now, as I showed you here, this is the same case as this situation. So you can just simply say x equals 8. So what I'm trying to show you here is that when you're solving equations for exponents, always try to make the base same. Okay, now we will go over rational exponents. Yes, here we go, this small part. This small section, as squared in red, is a very important section, and we'll introduce a little more about this when I explain rules for roots, because this is kind of a root topic. But I will just briefly go over this real quick. As we saw before, a to the power of minus n is a n over 1. But exponential fractions such as a to the power of 1 over n can be written as nth root of a. Now, this is really important, and this is also one of the most common mistakes people make. So you have to make sure you understand the difference between this guy and this guy. They're completely different things, and you have to make sure you don't get confused. The reason why people get confused is that because the fraction is in top of here, people think, oh yeah, I should just make it into a fraction like this. But this is wrong. You only make a fraction if there's a negative value on the exponent. So I'll just erase this real quick. And so if you look at this specific example here, usage of index law states that u to the power of 1 over 2 multiply u equals u to the power of 2 over 3. Now this can be written as here. This is a little big jump, so I'll try to solve this out for you. U to the power of 1 over 2 multiplied by u is u to the power of 1 over 2 plus 1, as I showed you here, the rule here, this guy right here. So this can be actually written as u to the power of 2 over 3. However, as I introduced here, the denominator of the fraction in the exponents becomes the power of this number. So this can be actually written as 2 root u to the power of 3, because this guy is just a single exponent. We don't treat that as a different thing. Can be written as square multiply u. But we all know, since they have the same exponents, this guy can go out of the root, so it becomes u root u. So this is the steps of what this is trying to say. And here it says a very brief, easy way to understand. If there's a exponent where it says a to the power of n over n, the n becomes the nth root, and n just becomes the power of a. So a first or n root a first doesn't really matter, as I said before. Yeah. So this here just means that you can write a_m to the root over n, or you can write a root n over n. They don't really have much difference. Okay, now we can just do this practice question real quick. I know the answer is really written here, but if you look here, as my friend Wani noted, simplify so you don't have to manually calculate things like a to the power of 4. Now, simplifying is a really good method, and I think for any exponent problem, you should always change the base to its fundamental state to make the question more easier. So by fundamental state, I mean changing 32 into this 2 over 5 and 8 to 2 over 3. This type of changing back really helps you out in the questions, so I recommend you doing it. And doing few practice questions of exponents before you go to exam is really helpful, because you can remember the rules again. Even though you think you know the rules, you may have forget, or you may get confused with log rules, because they are kind of similar and they're confusing. So please try to practice out some of the questions we will give out in the documents section, and that will really help you out for the test. Next, we will look at logarithms. Only need to know base 10. Yes. The logarithm of a positive number is the power that 10 must be raised 2 in order to obtain the number. Now this can be this can be understood as a very confusing concept, but it's not really confusing, so I'll just teach you real quick. My Wani friend again wrote a very good note here. Uh, when there's a notation saying 10 to the power of a is b, you can simply write log b to b equals a. So what power of 10 makes b? If log 10 is 1, it just means 10 to the power of 1 is 10. And if it says log 1 is 0, it just means 10 to the power of 0 is 1. And here, if the log 100, it's 10 to the power of 2, so it just becomes 2. So this number comes here. Now, logarithm can't come out really difficultly in this test, and we will look at the different notes here later, but these three are the fundamental rules of logarithm. Log is a very special mathematical notation as it shows how much power the number has. It has a direct relationship with exponents, and at the same time, it is really good because logs can become difficult once you mastered it once. So they always play in their own league, and it can't come out as difficult. Now, the only difficult thing is just understanding the concept at first. Yes, that can be a little difficult, I understand. But these three are the fundamental rules of log. I know there's about two more, but that comes out in DP or your future 10th, 11th grade high school math, so you don't have to care about that now. Yes, these three laws are pretty self-explanatory. If there are log multiplications, you can expand them into plus. Um, one thing you should always make sure, oh, that's a really bad spelling. One thing you should always make sure is that you don't get confused of the inner side and the outer side. For instance, this cannot be written as log A multiplied by log B. This is not true. So you have to also always remember how the log function works and understand that only these functions can be written this way and not the other way around. I'm just pointing this out because this is one of the mistakes I used to make. Oh yes, this is a really good point, so I'll just make sure I point this out. The exponent inside log, so the number that is inside log, so the n here has to be always bigger than 0. There is no way this can be written as 0. There is no way. It cannot be a minus, it cannot be a 0 in any situation possible. There is no way possible, so you have to also always consider that a cannot be negative nor 0. Now, as you can see here, do not use log a multiplied by log b is log ab. This is what I mentioned earlier, that different type of rules that you have to not confuse from. So understand that they have their own methods, and don't think about the other fundamental ways you learn. Just think about these different rules and you will be okay. Now, using logarithms to solve exponential equations. We cannot solve exponential equations such as 2x equals 7 by writing both sides with the same base. But we have seen that we can solve these equations graphically. Another option is to take the logarithm of both sides of the equation and then apply the logarithm law to find the equation. So as a solution given here, you can log is a type of writing the same equation differently, so you don't have to consider about would this change the value. It is the same as if there was 2x equals 7, the same as just adding 1 on each side. So putting log doesn't change the fundamental values of the equation, so you don't have to think a lot. You just have to make sure that you're putting on the both side. So log 2x equals log 7. Because of the exponent rule here, this guy right here, the exponent will go down, and as you can see, it's written as x multiplied by log 2 equals log 7. So x is log 2 over log 7. This will give you 2.81 as graphical calculator. So this would be an example of how you could solve log. if log with different powers come out, one thing that can come out is ln. And this is an optional concept, so you guys, for the people who are very busy and in a hurry to learn every concept, you guys can just skip this part. Ln just means it's log to the power of e. And what is e? E is the natural fundamental number of recursion. So this is a number that proposedly nature likes the most. That's kind of ironic because nature is not alive, but that is true. So this number e found by Euler is about 2.71828, and this can be characterized in many ways. It is the base of natural logarithm. It is limit as n approaches to infinity, but I know limit is way too early in your age to learn, so I'll just go. You guys just have to understand that there is a value of e, and you can calculate it. If ln comes out, it just means it's log to the power of e. And you guys, the function is in the calculator, so they won't make you calculate ln by hand. So you just have to understand that, oh, I see ln, it means log e. I'll just use calculator to find whatever the value asks for. So you just have to understand that. Not that difficult. But logarithm, if you learn at first, can be very confusing. So I recommend practicing a lot of different questions. So to check yourself how much you know. And one method I want to tell you is just prepare 10 easy questions and see if you can get all the 10 right. If you have one wrong, that means that you don't know something. So solve another 10 until you get 10 right in a row, and then move on to the middle level questions. In my opinion, this is about a middle level question for you guys. Really good helpful source would be our document and past paper exams. So try those things out and you'll be okay. For sets of numbers, you have a total of 7 concepts you need to know. So now in this subtopic, we'll be exploring natural numbers, integers, positive and negative integers, rational and irrational number, and real numbers. First, we will look at natural numbers, and this n here is a universal number, not number, notation to represent natural numbers. So these notations are all real notations, so you guys can use them if you were to express a range. I'll talk about that a little later, so don't worry. Um, the natural numbers, which are all of the positive numbers that are whole, is just written as 0, 1, 2, 3, 4, 5, 6. One thing the ironic is the definition is written as positive whole numbers, but 0 goes in. 0 does not technically have a negative or a plus sign, but 0 goes into the section of natural numbers. Next, we have integers, which are whole numbers that both positive and negatives exist. So these are examples. You guys have to make sure that for integers, there are no fractions. So 3 over 2 is not an integer. Wait, that's a bad Z. Yeah. And you guys also have to understand that if the notation is written this way, this is still a integers because 3 over 6 can be written as 2. And 2 is an integer number, as you can see here. Positive integer just means that it's integer numbers that are positive, and negative integer number is just minus 1, minus 2, minus 3, all negative integers. Notice how both of them don't have the number 0. That's because 0 technically is not a negative number, nor is it not a positive number. 0 just means there are no values, so there is no positive or negative. Now, next we will look at rational numbers, and these numbers are any type of numbers which can be written in the form p over q, where p and q are integers and q is not 0. Make sure you understand that q cannot be 0. If the denominator q is actually 0, so if there's a number of 2 to the power of 0, this is non-existing number. This does not go into the category of any number introduced, any section introduced here. It's not integer, it's not rational numbers, it's not irrational numbers, and it's not real numbers. It's just numbers that do not exist. So if there's a question asking you to categorize the different numbers in their subsections here, this will become an integer, this will become a rational number, but this 2 over 0 is non-existent number. So this number will not go into any categories. So make sure that. And a Q naught is also called the set of all irrational numbers like root 2 and root to the power of 3, 7, and pi. So the thing about people asking like what is irrational, how do you know if it's irrational number, is if you can represent it as a fraction, that's rational. If you cannot represent as a fraction, but the number goes into a factorial number, then that's irrational. So what I'm trying to say here is, for instance, we have this number 0.33333 to the power of infinity. This can be written as 1 over 3. So it is actually rational, as we can represent it as a fraction. However, numbers such as root 2, which would be 1.415 yada 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 yada, this cannot be written as any fractional number where q is a integer. So this would become a irrational number. So this is how you can try to think of it. And finally, we have the sets of real numbers, which are all numbers which can be placed on the number line. As you see here, bringing back this guy 2 over 0, 2 over 0 just does not exist in any number line here. So it's a number that does not exist. That was what I was trying to imply, and through the number line you can see it more clearly. Now let's look at a few of the notes my friend written here. Number that cannot be written in the form of p over q, where p, q are integers, and q is not 0, hence they cannot be simplified to a fixed number of digits. Yes, that's what I was saying. If you want to find the difference between irrational and rational number, you can simply think of it as, can I write it into a fraction of integer numbers? If so, that is rational. If not, that's irrational. All right, that's pretty much just a way to classify numbers, so you guys can just memorize this part. I mean, if you keep on practicing, you just understand it because the question gives you what is the integer value of, I don't know, 2 multiplied by 5, that'd be 10. So, yes, these are terms you get used to it. Just know what the number is, what the question is asking for when the question states irrational, rational, or integer numbers. That's all you need to know about here. Now, using algebraic techniques. Now, this is where the unit gets more fun. So first we have distributive properties here. This guy. When you're given an expression in the form of A multiplied by B plus C, you can simply change it to AB plus AC, where you're distributed into each terms in the bracket. So if I were to write 2 multiplied by x plus c, this would become 2x plus 2c. You can, if you want me to actually show you how it works, I can. For instance, if I have 2 multiplied by 4 plus 6, this would be 2 multiplied by, no, this would be, I would write as 2 multiplied 4 plus 2 multiplied by 6. Before you can actually just calculate it by 2 multiplied, adding 4 plus 6, that is 10. And if you write that down, it's 8 plus 12. So both values show the same result. So you can just understand that you can write it in this notation, this way. This comes out a lot in different algebraic components. So you guys have to understand this concept very well. Know this concept very well. Now, next we have expanding brackets, FOIL, for more than 2 brackets or 2 terms. This is the most basic form of the distributive property that can be expanded from other bracket forms. One of the most common example here is a plus b multiplied by c plus d. In this case, it's useful to use FOIL, a skill my friend wrote really well here. So the FOIL stands for first, outside, inside, last. So I'll just write that out for you. First, no, let's make it better by highlighting the first letters. First, outside, inside, and last. So this is the FOIL rule. And what this means by what this equation is trying to imply is that you can first multiply the insides together. Not the You can first multiply the first parts here, a and c, together, which will create AC. And you can do the outside, which is a and d, the outer layer numbers. And next you'll do BC, the insides. BC, the insides. And finally, you'll do the last terms. Now, if this is a little confusing for you, you can also understand it in a different way, which is writing the notation of a plus b multiplied by c plus d. But here you expanded using your mathematical knowledge from the previous distributive property. So you can just write it as a multiplied by c plus d plus b multiplied by c plus this. This also works as you can see, it becomes AC plus AD plus BC plus BD. Whatever suits you, Owen. As you can see, the two properties are the same. You can just use the method that suits you the most. Now, as you can see here, my friend Wani has done a great job on representing this geometrically using rectangles. This rectangle here represents the distributive properties shown here. As you can see, one side represents A, the number getting multiplied by, and the side B plus C is this side right here. So you can just write it as AB plus AC, as area is side multiplied by side. So that's a easy way to understand distributive property. And when you have more than two terms in a bracket, you can first multiply the numbers in the first bracket by every number in the second bracket, adding them up as you go. Then repeat the same process with the second number in the first bracket, so you multiply out with every number in the first bracket as well. Now that I just gave you a really confusing explanation, but you can just think of it as looking at the diagram here. If I were to multiply A and C, if I were to solve this equation, I would first write down the sides A, B, and then I'll write down the sides of C plus D plus E, the bracket here. And I would first write all the A terms and write them down here as AC plus AD plus AE. And then I'll move on to the side B, where I will write down plus BC plus BD plus BE. Yes, that's how you will see it. The thing about here is, no, the question will never, I won't guarantee never, but they will not probably ask you in the format of this way. But the reason why we're introducing you this concept is so that if there were to be a complicated expansion like this, you guys won't freak out, and you guys can remember maybe the rectangle rule or the expansion rule to expand the brackets calmly and don't get confused. This skill also comes to you in handy when you're solving different different quadratic equations that will be introduced later. So make sure you understand this concept very well. Now, the difference of two square rule is a pretty common used one. And if you see as the expression is written in the form a squared minus b squared, you can change it into a minus b multiplied by a plus b, vice versa. You'll find that if you actually expand those brackets, you'll get the same results as the book. This is a screenshot from the book states. So, yes, the middle term adds to 0, so the only thing you're left out is a squared minus b squared. Now, my friend has written here a very good example. So, as you can see, there is 2x minus 1 over 2x minus 1 plus 4x squared minus 1. Now, this is a very difficult equation to just expand with nothing. So, we're going to try to change this equation in an easier way. Notice how these small equation here is actually written in the form of a squared minus b squared. In this case, b would be 1 and a would be 2x. So if I look at the equation and try to expand it, this 4x squared minus 1 will actually become 2x minus 1 plus 2x plus b not b plus 1 multiplied by 2x minus 1. Now make sure you don't get confused and write plus here. That's different. It has to be multiplication. And if you see it this way, you can notice how the two numerator constants have 2x minus 1 here. So we can erase them together to get 1 over 1 plus 2x plus 1. That becomes just 2x plus 2. Yes, this is what it's showing. And in my opinion, this is a pretty easy skill. So you guys have to master it. Now we will look at binomial expansions. Yes, in the MYP, the only thing you need to know about binomial expansion is how to expand them and identify their coefficients. The basic rule is that for every expansion in the form of a plus b to the power of n, ignoring the coefficients of the term yet, they become a to the power of n plus a to the power of n minus 1 minus b plus n to the power of n minus 2 multiplied by b to the power square, yada 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 until b to the power a multiplied by b to the power of n minus 1, and finally we have b to the power of n. Notice how for each expansion the power of a is reducing by 1 and b is increasing by 1. So at the end here to the b to the power of n, there would be actually a to the power of 0, but this would be just 1, so it's neglectable, so we didn't write it. This is how you expand the equation, so you guys have to just understand that. A great example is here. Ignoring the coefficients yet, as I said, you can see how it starts with the same power of n, a to the power of 3, and then it goes as 1 decrease, n minus 1, a to the power of 2 multiplied by b, plus a to the power of 1 multiplied by b to the power of 2, and finally we have a to the power of 0 multiplied by b to the power of 3. Now we will look at the Pascal's triangle to explain the coefficients. Now, for the coefficients, simply follow the Pascal triangle. In MYP, you're usually tested in smaller orders expansions, so just memorize the first four or five rows, and that's more than enough. The numbers in the row tell you the number of coefficients for each term in expansion. So let's see. As my friend wrote here, you can just read over this, but I'll give you a specific example. For instance, if we have a to the b a plus b to the power of 4. You will first write, as I said, for the expansion, you will write a to the power of n, so it's a to the power of 4, plus a to the power of n minus 1, that's 3, multiplied by b, plus a to the power of n minus 2, that's 2, multiplied by b squared, plus a to the power of 1, multiplied by b to the power of 3, plus a to the power of 0, b to the power of 4. But a to the 1, since a to the power of 0 is just 1, I'll just write b to the power of 4. Now, looking at the Pascal triangle, I know since the coefficient is 4, I have to look at the fourth floor. So that's 1, 2, 3, and fourth floor. And these are the numbers of the coefficients. So I will know it will be 1 multiplied a to the power of 4 plus 4 multiplied a to the power of 3 multiplied by b plus, what is it? 6. 6 multiplied by a to the square, a squared, b squared plus 4 multiplied by ab to the power of 3, and finally 1 again, so it's 1 multiplied by b to the power of 4. So the whole equation can be written as a to the power of 4 plus 4a to the power of 3b plus 6a to the power of 2 b to the power of 2 plus 4a b to the power of 3 plus b to the power of 4. That's a lot of power I'm speaking. Yes, also one thing you have to make sure is when it's a minus b, simply don't get confused and just change the a minus b into a plus minus b, and then you'll be fine. You can just simply treat minus b as the real b here. So instead of putting b here, I would, if this was to be a minus b case, I would change it to minus b bracket. So yeah, that's one thing you can do. Or you can memorize in a way of putting plus signs with a minus sign for every other every one steps. What I'm trying to say here is if this were to be a minus 4, I would still expand it in the a plus b form, and then at final I would just change every second, fourth, sixth term into minus, and that would still work. But this method is more fundamental and simple, so try to use this way and you guys will be okay. Now we have simplifying radicals. These laws of radical or roots are also important to know. These are pretty straightforwardly written here. Root a multiplied by root a is just a. This is squaring of a root, which cancels it out. Next, we have root a multiplied by root b, which just becomes root ab. If you have a multiplication of two roots, just put the two things inside the roots under one single root multiplied by together. Now, next we have the division rule right here. Just like the multiplication rule, if they are on the same roots, you can just put them in the same roof. This would be better to understand if you know the fundamental concept of root, as I introduced before on exponents rule here. Right here. The nth root is n root a. So the thing about root is that it's just notated as a to the power of 1 over 2. It's the same thing. So if you think about it, if I were to multiply a to the power of 1 over 2 and b to the power of 1 over 2, because since they have the same exponents here, they would just become ab to the power of 1 over 2. If I were to write it in a to the power of 1 over 2 over b to the power of 1 over 2, I can just simply bracket them whole and write it this format. And now I'll just tell you some simple rule here. My friend wrote it down really small here, but this is also a very important concept, so you guys have to know. What this equation is trying to tell you is that you can treat root like a variable. So what is it? So what it's saying here is that if you don't know the specific value of root a, you can just treat it like it's an actual variable. I know my friend used x and y here, so it's confusing, but instead I'll just write it in notation of, well, let's say 2 root x, no, let's say there's 2 root 3 plus 5 root 3. We don't know the specific values for root 3 because, as I said before, these are irrational numbers where we can't think of the specific ending. So I'm going to treat root 3 like a variable. So in this case, a will become 3. So root 3 equals x. Now, 2 root 3 plus 5 root 3 would become 2x plus 5x. And what is this? This just results in 7x. So it could be just written as 7 root 3. So this is what I'm thinking about roots as variables, even though they're actual constants. So make sure to change back if you're going to use this rule, and exponents would be fine. The thing here is written down here below is just for further reference on how to use roots and their fundamental concepts. As you can be seeing here, since these are power, it will, as I said, since roots are to the power of 1 over 2, it would just be 2 multiplied by 1 over 2, which just becomes 3. So the 3 can come out. This is a pretty straightforward rule, so I don't think I need to explain any further. I'll just leave this for your sake. But these are not difficult, so just read over and remember what you learned in mathematics class. This is a simple tree diagram to represent the factors of 72. If you guys are uncomfortable or do you feel like this takes too much time, you can simply do the opposite division rule, which you write the 72 and you do opposite division. So you think of the first most smallest value you can divide, which for me it currently is 2, besides 1, because 1 is every factor for 1 is factor for every number. So if you multiply 2 by 72, you get 36. The next number I'll think of is 2 again, because 2 is still divisible. That'd be 18. 18 is still divisible by 2, 9. Now, since it's not divisible by 2 and doesn't give a concrete integer number as it ends, I'll move on to the next smallest number, which is 3. So if I multiply by 3, you leave with another 3. So you just have to simply look at the outside, and this will become your factor. So if you write it out, that is 2 to the power of 3, because there is 1, 2, 3 2's, and you have 3 to the power of 2 because there's 1, 2 3's. So these are different ways you can factor. And prime factorization will always help you solving roots, so make sure you do that. Okay, continuing on now, we have rationalizing the denominator. Conventionally, you're required to simplify by rationalizing the denominator in your answer. Now, before I introduce the ways to rationalize the denominator, I will kind of explain why we need to rationalize the denominator. Beforehand, on the previous part of the video, I introduced how root 2 and pi are certain numbers that are irrational numbers. So these are technically numbers that doesn't have a concrete value we can determine. Unlike 1 over 3, which we know 1 over 3 is just 1 out of 3 pieces. So these are actually concrete numbers that we can pinpoint the exact value, but root 2 and pi are infinitely converging numbers that we don't know the exact value, as it goes on and on and on without a pattern. So then why is this a problem when if you have it as a denominator? The thing about these kind of irrational numbers is that because they don't have a concrete value, we don't know how many, like what exactly the value is. So just bringing the example here of 14 over 3 minus root 2, in order to know the value of this number, we have to know the denominator. We have to know how many are we talking about as a whole. Because technically fraction, as introduced in the first part of the very first part of the video, is actually a ratio, and it's also the percentage. So we have to know the total possible outcomes in order to know the how many are possible, which is the numerator. So in order to determine a value of fraction, we have to have the denominator as a concrete rational number. However, root 2, as I explained before, is an irrational number, meaning we can't technically know the exact value. So it's very important in your grades to actually rationalize the denominator in order to make this into a value that we can determine. Now, yes, you can just read over the concept here. You can look at the example and try to solve it. Don't worry, I'll do another example and give you a thorough guide through of where and how to exactly do the steps. Now, I'll just think of a really easy example here. Yeah, let's do 16 over 2 minus root 3. Now, as I said before, since root 3 is an irrational number, we have to rationalize the denominator part. Now, and to do so, we're going to actually bring back a rule that we learned before, which is here, the perfect squares. Yes, this is the equation that states that a plus b multiplied by a minus b leads to a squared minus b squared. Now what we're going to try to think of is, first I'm just going to bring the equation right here so that we can easily notice equals a squared minus b squared. And I'm going to think that 2 minus root 3 is actually this side here right now. So I would think that A is 2 and B is root 3. Now what that allows us to do is we can actually multiply A plus B here, and then we will result in getting A squared minus B squared. Now what I mean by this is I'm going to multiply 2 plus root 3 because that's A plus B over, since this is a fraction, you have to also multiply the same number on the numerator side. So multiply by 2 plus root 3. So in total, you'd be just actually multiplying 1. Now, what this leads is, as I said about the perfect square rule, this would actually just create 2 squared minus root 3 squared over 16 multiplied by 2 plus root 3. Now what this is actually it's 4 minus 3 over 32 plus 16 root 3. Now our denominator is actually rationalized as it's now 1 over 32 plus 16 root 3. So we can actually represent the number this way. Now this is a common number that we can actually determine the value of. So this is how you can rationalize the denominators by thinking of the a plus b multiplied by a minus b equals a squared minus b. This b squared. This is the concept we're using here. And don't get confused if the number shows up as, for instance, 2 over 5 plus root 2, because it just means that in the a plus b multiplied by a minus b, instead of using the a minus b section, we're using the a plus b. So a would still be 5 and b will be root 2. So you'll multiply a minus b, which is 5 minus root 2. And don't forget always to multiply the same number on the top, or else the value itself of the fraction changes. That's all you need to know for rational conjugation. Honestly, the unit number 1 is more about memorization than actual mathematical concepts. You're learning the different methods to solve the questions. You're learning what tools you have and what methods you have in order to solve this question. So it's very important that you fully understand and fully memorize to a certain extent um, uh, to solve the questions. But one thing to make sure is that you don't really need to fully try to memorize the whole equations, like for instance, memorizing a date for a history class, because as you solve the questions, your hand gets used to it and your body remembers these steps. So rather than just spending time on memorizing these different equations, I recommend just solving a lot of practice questions, and the memorization will just come as you practice the numbers, so you don't have to be concerned about it. One thing, again, I didn't mention here is that for numbers that are represented as root a over b, you can just simply multiply root a on both sides, and then that will give you a over b root a. So if it's not written in a plus or minus equation, and it's just a solo root, for instance, 5 over root 2, that's a really bad looking 5. 5 over root 2, you can just multiply root 2 on denominator and the numerator, and that would give you 2 over 5 root 2. So this is another way you can rationalize the denominator. We're going to move on to a little more, in my opinion, fun part of this unit, which is solving quadratics. To be honest, I feel like solving quadratics is like the fundamental, like the very basic part of mathematics, because as you learn calculus and integration, you learn how much these finding the quadratic, solving the quadratics is important, and understanding quadratic itself is also very important. So I'll be introducing you to the different methods, so you just have to follow along right now. We're almost halfway through, so stay tight. Solving quadratics. We'll start with factorization. Factorization is when you break the number down into smaller numbers that multiply together to give you that original number. I introduced this while I was explaining root right here. This is also factorization. Now, one thing different from the factorization we did before is that this factorization is factorization of different equations. So instead of factorizing a single integer or a rational number of 72, 36, 24, yeah, dot, 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 we're factorizing equations like x squared plus 5x plus 4, x squared plus 3x plus 2, like this. We're trying to factorize the equation. As introduced here, we're trying to factorize the form of ax squared plus bx plus c. Now, how to do this is by completing the squares. Now, let's look more deep into it. Factorization may seem difficult at first, but it's not really complicated. My friend Wani here did a really good way of representing the diagrams. So if you look at the example here, we're looking at x squared plus 7x plus 10. Okay, so what my friend Wani did here is the cross method. Now, what he's doing is, for instance, if there's an equation of 2x squared minus 13 plus 15, we're trying to divide the equation into two parts. Now, if you think about it, if there's an equation written as a squared plus bx plus c, this can be actually written as two multiplications of different linear equation with only x to the power of 1, fx plus g. Now, assuming every letter here besides x is constant, we're assuming that a multiplied by a, no, we're not assuming. We know that a is actually d multiplied by f. Bringing back expanding by brackets, if you write down the form of this this equation, it will become actually, let me actually just erase this for right now. It would actually just become dfx squared, because first we have to do these two, and plus dgx plus, now we'll do the bottom side, which is here. We have efx plus eg. Yeah. So now we know that this equals ax squared plus bx plus c. So what this means that actually a is df and b is dg plus ef and c is eg. Now this may look very, very confusing with different type of letters, but if you understand this right now and just look at this cross product diagram, you'll understand. So here we can understand that currently d and the number 2 is d here, this guy's d, and f is 1. So because a here is 2, we have to know that d multiplied by e has to be 2. So these two numbers here has to multiply and result into a, and these two multiplication has to result into c. So if you look at it, as you can see, 2 multiplied by 1 is actually 2, minus 3 multiplied by minus 5 is actually 15. Now, the special thing is the middle part, which is b and which is dg plus ef. So if you look at it, currently we're considering d as 2, e as minus 3, f is 1, and g is minus 5. Oh, sorry, I have written it a little wrong because there's so little space here. Here, there we go. As you can see, as I said, dg plus ef. So let's see. Minus dg, which is 2 multiplied by minus 5, plus minus 3 multiplied by 1. This will result in 10 minus 3, which is minus 13. And as you see, this is resulting the same value as the B alphabet here. Now, you may be a little confused because I used too many letters here, and I know that's pretty confusing, but this is the most fundamental way to explain. The cross-sectional method is always a good tool for you to factorize quadratic equations. So certain equations like x squared plus 5x plus 4, we know that since a here is 1, since I'll just write the equation format here too, just for you to understand it better. Since we know a is 1 here, we know the first part of the equation will just become x and x. Because I want to write it into a cross, I know since c is 4, I know multiplication of the two variable, no, I'm not going to write it. Two variables here would actually turn out to be multiplication of the two variables here will turn out to be 4. Now, what we have to think is that because we want to match out this equation format of dg plus ef is b, which is 5 here, since we know d and e here is actually 1. Oh, wait, no. Since we know d and f here is actually just 1, we know this equation just becomes g plus e equals 5. So now we have to think, we know g multiplied by e is 4, and we know g plus e is 5. What could be a number that results in that? We can simply think it's 4 and 1, because 4 multiplied by 1 is 4, and 4 plus 1 is 5. So this will just result in x squared plus 5x plus c, not plus c, plus 4 is dx plus e multiplied by fx plus g. But now we know what the alphabets mean. D is 1, so d is 1, and e is 4. So I'm just going to write x plus 4 multiplied by x plus 1. So this will result in the same value. You don't have to be confused about which one has to be 4 and which one has to be 1. It doesn't really matter. Even though you write x plus 1 multiplied by x plus 4, they give you the same results. It's the same as writing, for instance, 6 is 3 multiplied by 2. But 2 multiplied by 3 is also 6. So you can write the equation in different ways. I know these letters are pretty confusing, but I hope you guys kind of get a sense of how to use these cross-sectional methods. But the best way to understand is just know that quadratic equation ends up in two linear equations. And to get that two linear equation, you have to know that in this diagram here, a multiplied by b is q, and a plus b has to be p in this format. And this is due to the expansion of brackets I introduced up here. We have it right here, this guy. So understanding that bracket expansion helps you understand the concepts we're trying to use here. And it's not fairly difficult, so try to understand. And if it's too confusing, I hope you can ask your teacher about this, because this is a very important section of quadratics. And I can 99% guarantee at least one question will come out regarding solving a quadratic. So you guys have to understand this. So next, you're to look for the difference of two squares. So what this is talking about is what I'm doing here. So what are you going to do next? You're going to try to know what is the multiplication of the different numeric numbers, and you're going to try to find the grouping in pairs and the sum and the product type. Now these 5 are not numbered steps. It's not that you have to do this first, second, third, fourth, fifth. These are all individual methods you can use to find the factorization of the equation. So I recommend you understand all these 5 different ways. Next, we'll be moving on to completing the square. Completing the square is a technique for rewriting quadratics in the form of a multiplied by x plus b to the power of 2 plus c. Now, to avoid confusion with the previous notation we used, which is ax squared plus bx plus c, I will try my best to use the notation ax plus q to the power of 2 plus p, because b and c, if I were to write it in the format of ax plus b to the power of 2 plus c, you might think these two numbers are the same, but they are not. So make sure you don't get confused with that. A is, though, the same number because you're just taking out the coefficient. So they're the same, but since b and the b here and the c here is actually different, I'll just write it instead of using b or c, I'll just write it as p or q, so you guys can understand it more easily. Now let's look at in depth with the steps. Some quadratic equations, such as x squared plus 4x minus 7 equals 0, cannot be solved using the factorization method. Now, this is very important. This will also be introduced in your future lessons in DP where you learn integration. But when solving mathematics, there's always steps. There's the first method you should try, the second method you should try, and the third method you should try. So in solving quadratic, always the first method is the cross method or the factorization method, as my friend Wani here called it. Why do you have to do the cross method first? The thing about cross method is that it's the most easiest way. And if you the thing you notice about cross method is that the numbers always come out as rational numbers. So you always understand that the answer or the point where x reaches y equals 0 is actually just easy rational numbers. Now, because rational numbers are, as I said, numbers with specific values that we can determine, um, these are easy to figure out. But as the question says here, there are certain equations that you cannot use the factorization method. As you can see, you know the factor of 7 is 7 and 1, but there's no way you can make 4 with 7 and 1 by using the cross method. So you have to understand that for some equation, you cannot use the cross method, but you have to make sure you have to try the cross method first because they are always the most easiest way. Second method here is completing the square. So here about completing square is we're trying to create a complete square using the numbers that we have. Now, what we're trying to do here of completing the squares is changing the equation. Let's use the example here. The example here we have x squared plus 4x minus 7. And we know, as I said before, we know this can't be solved with cross method. So we're going to try to create it into a perfect square. Now what we're trying to do is, since we know x squared plus 4x can become a perfect square, we're going to move the 7 to the other hand of the right hand side. And then we know how x squared plus 4x can be a complete square. So we're going to try to add 4 on both sides to create this number into a perfect square, because we know x plus 2 squared is x squared plus 4x plus 4. Now here we're missing that plus 4, so we're adding plus 4, but because we don't want to change the whole value of the equation, we're adding plus 4 on the other side too. Now this becomes x plus 2 squared, which equals 11. If we try to solve this for x, we'll get x plus 2 equals plus minus root 11. X equals minus 2 plus minus root 11. Now notice how these plus minus is not actually just a notation saying plus minus, but this means that the one solution is minus 2 plus root 11, and the other solution is minus 2 minus root 11. You guys have to know the difference between these two. Okay. And yes, this is the exact same thing I did, and as you can see, it gives you the same answer. Now, to complete a perfect square number, we must add both sides by having the coefficient of x, then sharing this value. What this means that is we're trying to find the b squared over 4 value. Now, you might get confused as what are we talking about right now? What we're trying to say is, for instance, if you look at this equation, we have x squared plus 3x. Wait, no, I'll just try to solve this in my own way and explain together. By the way, even though I'm using my own way to solve it, just because I want to guide you through it, it doesn't mean that this diagram is wrong or this diagram is bad. This diagram has been made by my friend Wani, and it's very thorough and clear. So I hope you guys, when you guys are trying to review before a test, look at Wani's notes and understand, oh yeah, there was a method like this. So what we're trying to do is x squared plus 3x minus 3 is 0. And as I said before, because we want to make this part of the equation into a perfect square, we're going to move the minus 3 to the other left. We're going to try to move the left-hand side minus 3 into the right, now becoming plus 3. However, we don't specifically know the complete how to make this into a complete square. Like beforehand, we had x squared plus 4x, which was obvious just by adding 4. We will create this into x plus 2 to the power of square 2. We will turn it into x plus 2 to the power of 2. Now, one thing about complete square quadratics is that you can write it in the format of a multiplied by x plus q squared, as I introduced before here. Now, the thing about this equation, if you expand it, you actually receive a multiplied by x squared plus 2qx plus q squared, bracket closed. Yep. So notice how we're trying to get this equation format for x plus 3x. Then what that means is that 3x is actually 2qx. They're the same thing. So if you write it in that way, I will write 3 equals 2q because x is just a variable. And then now we can get q, which is 2 over 3. Then now we know what to add, which is q squared. So if we add q squared on both sides, we get x squared plus 3x plus 4 over 9, since q squared is 4 over 9, equals 3 plus 4 over 9. Notice how this x squared plus 3x plus 9 over 4 is now exactly written in the format of x squared plus 2qx plus q squared. So because we know q, we can write this equation in terms of perfect square, which is x plus q, which is 2 over 3 squared. So if you solve this fraction, you will get 4 over 21. So x plus 2 over 3 is plus minus root 21 over 4. Notice how you can just write this as plus minus 2 over root 21 because 4 is actually 2 squared. So the square gets cancelled out and you can take the 2 outside of the root. So if you write the full answer, it would just become x equals minus 2 over 3 plus minus root 21 over 2. Yes. And as you can see, it's the same. So this is pretty much how you can use completing the square to solve the equation. Now there's a similar way, actually a easier way of using this completing the squares, but actually using the quadratic formula. Now this quadratic formula is given to you as a very good idea to memorize. Like the equation of the formula itself is minus b plus minus root b squared minus 4ac over 2a when the equation is written in ax squared plus bx plus c equals 0 4. Now make sure you see, it might look like it's a very difficult equation to memorize, but it surely isn't compared to the other equations you will memorize in DP. So I hope you don't get too stressed about that. And one thing you have to make sure is that if you want to use this equation as the letter numbers here written, you have to know that this equation only works when the equation is written in this ax squared plus bx plus c format. So you have to make sure you expand the equation if it's not written in that form. For example, if you have an equation of 2x squared minus 7x plus 1, just by, as I said before, first thing you have to check is if you can use the cross product method. Just by looking at looking with our eyes, we know we can't use the cross product method because we can see how we cannot make minus 7 out of multiplication of 2 and 1. So we're gonna turn our side towards the quadratic formula equation or completing the squares if that makes you if you feel more comfortable with that one. But if you look at since we know the equation is currently written in the format of ax squared plus bx plus c, we know here that a is 2, b is minus 7. You have to put the minus, make sure that to do that, and c is 1. So all we have to do now is just plug the numbers according to the letters. Because it's minus minus b, because it becomes minus minus 7, the value becomes just positive 7. So it's 7 plus minus root 7 squared minus 4 multiplied a, which is 2 multiplied by 1, over 2a, which is 2 multiplied by 2. So it just becomes 7 plus minus root 49 minus 8 over 4, which becomes 7 plus minus root 41 over 4. So the answer would become 7 plus minus root 41 over 4. So this is actually, compared to how difficult the formula itself looks like, this is one of the most easiest way to solve a quadratic formula because I can guarantee you this equation works every time. But the one thing you have to really make sure is that the equation has to be written in this ax squared plus bx plus c format in order to solve for the equation. So just be aware of that and you'll be okay. Now we will move on to using discriminants to determine roots. The discriminants can be used to find how many roots a certain function has. So the book introduced you to a concept called delta. This is actually a Greek alphabet D, but it actually means change, but it's just an alphabet here, so you just have to understand that this just triangle means delta. So if delta is bigger than 0, it means that the quadratic equation has two distinct real solutions. And for when delta is 0, the quadratic equation has one real solution, which is x equals minus 2a over b, when the equation is written as ax squared plus bx plus c format. Now I can explain why this turns out to be like this, is because um, first you have to understand that delta is b squared minus 4ac. Now doesn't this look pretty familiar? Like really familiar? Yes. It's exactly the equation inside the root of the quadratic formula. Now the reason, because we're talking about if this is bigger than 0 or not, because if you think about it, if b squared minus 4ac is bigger than 0, it means that there is a value for this root, so there is at least 2, because there's plus and minus. So there's two values for the two distinct roots. However, think of b squared minus 4ac is 0. That means that the root just becomes 0. This whole part just becomes 0. So there would be no plus minus, so there will be only one solution, which is minus 2a over b. If you think about when b squared minus 4ac is lower than 0, it means that there is a minus inside a root, since this is lower than 0. That means that this value does not exist. We can't determine a value with that can be squared into minus. So we know the two solutions do not exist. That's what the book here doesn't have. You have to understand that if I'll just write this a little bit for you. B squared minus 4ac is lower than 0. It means there is no solution. Now, that was the algebraic way of explaining how to use this b squared minus 4ac. But my friend here, Vani, again, superstar, has written the graphical way of explaining it. As you can see, if delta b squared minus 4ac is bigger than 0, you get two real solutions here. If you have exactly 1, you just get one solution. And if it goes below 0, there is no solution. Now, the fun thing here is that the graphical way of representing is just actually, you're writing the graph as y equals ax squared plus bx plus c. The intersection between the x-axis is actually the solution that we're trying to find. So these are the way of determining how many roots the equation has. Now what we have next is solving for systems of equation. Systems of equation means solving for x and y when we have two equations using x and y. Two linear equation is the key point here. You have to have linear equation. If you have exponents equation, that becomes a little difficult. There are three ways of solving systems equations. One's by substitution, one's by elimination, and one's by graph. Now, if you look at it, the first method is by substitution, where we're trying to write, using one of the linear equations given, we're trying to eliminate a variable. So we're just going to try to write in terms of y or in terms of x. My friend here used in terms of y, and he has used the first equation and he rewrote it in terms of y, saying y equals 5 over 8 minus 5 over 4x. And by doing so, he instead of using the y here, he put the equation 5 over 8 minus 5 over 4x to explain the whole thing. Now, this is a pretty well written note, so I'm not going to write any further explanation or guide you through it because you can clearly see how he wrote the first equation in terms of y, then put the y value into the second equation to solve for x. And I think this is a really good method. So he has successfully solved y in terms of x and y. Now the second thing we have is by elimination. And elimination is actually one of my favorite methods. I use this method the most. It's by removing one variable. So if you see, we have two different equations, but with different coefficients. But what I'm going to try to do, what the elimination method wants us to do, is try to um, remove the variable by making the coefficients same. So here, my friend multiplied -6 in the first equation and got uh, minus 12x minus 6x minus 30, because if you multiply -6 in the whole term, you get that term. And if you see the equation below, you get minus 3x plus 6y. So if you add them together, you actually, the 6y's actually disappear together because the top equation has minus 6y and the bottom equation has 6y. And the only thing you're left over with is minus 15x equals minus 30. So you can simply just solve for x. This is a really easy method, but there is no answer to using which method to solve the equation. There is no better method. So you just have to choose what you want. But this by graph is kind of special. If you were to solve a question solving systems equation without a graph, it'd be rather just better to use elimination or substitution, because drawing graph takes a lot of time if you don't have a graphic calculator. But if you do have a graphic calculator, you can simply just graph the two equations on the same graph, and the intersection would be the point we're trying to find. The value of x would be 3, and the value of y would be 2. So my friend here wrote, if lines are parallel, then there are no solutions. If lines are perfectly overlapped, then there's infinitely many solutions. That is obvious because we're trying to find the intersection. If the lines are parallel, there is no intersection. And if the lines are overlapping, that means that all possible values are all the solutions. Now, the reason why we'll be using a graph is if we get an equation that is really, really long and really, really complex that nobody wants to actually try to use both the elimination method or the substitution. So if you were to get an equation like this, I would not even try to use substitution here. This is stupid. I would not try to solve this using substitution or elimination. So, wait, 15x minus 12y plus 7 over 12 plus a over 22 equals 0. Yeah, so I would not even try to use substitution, nor I would try to use elimination. I would just graph them right away and find their intersection. So make sure just to use the graph for when the equation is way too complex and you have a graphing calculator in your hand. That's the purpose of us introducing you the graph method. Now what we have here is my favorite part in the total field of math, which are sequence and series. Now the first thing I'm going to explain is the explicit formula, which gives the nth term of the sequence in terms of un. So un is just a representation of writing the nth term of a sequence. The explicit formula for the pattern of balls is un equals 2n minus 1. So if there were to be a sequence of number which is 1, 3, 5, 7, 9, dot, 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 we can simply understand that un will be 2n minus 1, because when n is 1, it would be 2 minus 1. When n is 2, it would be 4 minus 1. When n is 3, it'd be 6 minus 1. And you can see how the numbers have the right values for each nth value. So we can use this formula to find, for example, the 10th term of the sequence, which we can simply do it by finding u10, which is plugging in n and n by 10. So you get 2 multiplied 10 minus 1, which is 19. So this is the way of using explicit formula. So the thing about recursive is you don't need to be confused about the difference between explicit formula and recursive formula. Explicit formula just means that explicit formula is just using the nth term to represent the term you're in. But recursive formula is when you're just using the previous term to explain your current term. So if I were to write this equation in recursive formula form, I would say un is un minus 1, the previous term, plus 2. So since we know u1 is just 1, the second equation would be, no, not the second equation. The second term would be u2, which is u2 minus 1 plus 2, which is u1 plus 2, which is 1 plus 2, which is 3. Yeah, it's a kind of complicated, but this comes in handy if you can't determine the pattern in the sequence. And that kind of happens a lot in DP. So we're just teaching you this special method. And if I go on, u3 would be u3 minus 1 plus 2, and that be u2 plus 2, and that be 3 plus 2, so that would be 5. And then you can see how you're getting the right values here. So this is u1, u2, u3, da, 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 da. Now what the arithmetic sequence is that arithmetic sequence is a sequence of numbers such that difference of any two successive members of the sequence is constant. So what this means is that using the explanation of the Haese textbook, it says that it's in which each term differs with previous one by the same with fixed numbers having a common difference. Now it's really easy to see if you look at the example here. If you were to have a sequence of 1, 5, 9, 13, 17, dot, 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 this would be arithmetic sequence because you can see how for each term, we're just adding a 4 again and again. So u1 is 1, u2 is 1 plus 4, u3 is 1 plus 4 plus 4, and u4 is 1 plus 4 plus 4 plus 4. So you can see how each term is just increasing by 4. So the arithmetic sequence with first term u1 and common difference d, the general term of the equation can be written as un equals u1 plus n minus 1d. And in this example, you can see how u1 is just 1 because that's the first term. And un can be written as u1 plus n minus 1d, but d here is the common difference, which is 4. So it could be 4. And so the total equation, if you write it out, would be 4 multiplied n minus 1. Yes, this is the way you can represent it. And let's look at the notes my friend wrote here. Some sequence don't have a common ratio and a common difference. This sequence is non-arithmetic and also not geometric. Both R and D can be negative. So the R he's talking about is the thing that comes out next, which is the geometric sequence. But what this notes just states is that there are some sequences that don't have a pattern. For instance, 1, 3, 10, minus 2, 8, 6, 5. There is no pattern here. So this equation is not an arithmetic sequence nor a geometric sequence. It's just series of numbers. So this is what this this is what the note in red is trying to say. Geometric sequence is a sequence of numbers that follow a pattern where the next term is found by multiplying by a constant called the common ratio R. So it's just same as arithmetic sequence, but in this time you're not plusing, you're multiplying. So as the example gives here, we have a series of 2, 6, 18, 54, and we notice how u1 is 2, and u2 is 2 multiplied by 3, and u3 is 2 multiplied by 3 multiplied by 3, and u4 is 2 multiplied by 3 multiplied by 3 multiplied by 3. I think I can rap now, and so on. So the geometric sequence can be written in this equation, and if I were to find the equation format of this series, I would know that because u1 is 2 and r here is, we know it's 3, we know un can be written as u1 multiplied by rn minus 1, and that would be un equals 2 multiplied by 3 to the power of n minus 1. So if you see, this is the same value since the sequence was 2, 6, 18, 54. If we use the equation to get the nth term, when n is 1, it's to the power of 0, so it just becomes 2 multiplied 3 to the power of 0, which is 2 multiplied by 1, which is just 2. For the second one, we have 2 multiplied 3 to the power of 2 minus 1, which is 2 multiplied by 3 to the power of 1, which is 6. And for the third term, we have 2 multiplied by 3 to the power of 3 minus 1, which is 2 multiplied by 3 to the power of 2, which is 18, and so on. You can see how this equation represents this geometric series. Now, what I'm going to try to tell you is the difference between series and sequence. A series is the sum of the number of a sequence. So for a finite sequence of u1, u2, u3, un, with n terms corresponding to the series, u1 plus u2 plus u3 plus un would be the sum of the series, Sn. We write this in terms of Sn. So un is the nth term. Sn is Sn is the sum of all the terms until n. So this can be easily understood. So if you were to find the arithmetic series, so the sum of the arithmetic sequence, you can use the equation 2 over n to u1 plus n minus 1d. This is the fundamental equation of arithmetics. But there's another equation which is u1 plus un. Actually, the thing about this equation is that they're actually the same. So one equation states that Sn is 2 over n multiplied by u1 plus un. And the other equation states that 2 over n multiplied by 2u1 plus n minus 1d. You can notice how instead of writing un, you can use the equation I introduced you at top, which is u1 plus n minus 1d. So if I were to write that again, because I'll just write it again here because there's more space here. You can just simply use, I'm just going to erase this one, 2 over n multiplied by u1 plus u1 plus n minus 1d. And this is 2 over n multiplied by 2u1 plus n minus 1d. And so you can see how the two equations are the same. So you can use either equation. If you're given the final term, the nth term, use this equation because that's way more convenient. But if you're just given the initial term and the common difference, use the second equation to solve for the series of arithmetics. Next, we have sum of geometric sequence, which is geometric series. And geometric series have actually a very complicated equation, as you see. And this also, like arithmetic series, have two equations. And this also has both equations work. Now, Sn can be written as u1 multiplied by Rn minus 1 over R minus 1. Or it can be written as 1 minus R over u1 multiplied by 1 minus R to the power of n. Now, I won't be deriving this equation because that is a little complicated, but you have to make sure that you memorize all the equations that I introduced you for the arithmetic series, geometric series, and the sequences as well. So I won't be explaining about this equation a lot. I won't be explaining about this equation, but because I'll just show you how to use it when I'll be solving past paper questions, because I'm sure at least one question is going to ask you about one of the topics that I told you about sequence and series. So you have to make sure you have to study this topic properly. Now, the special case you have is sum of an infinite geometric series. Now, the infinite geometric series is a sum of the term of geometric sequence which continues infinitely. So example of the infinite geometric series includes 2 plus 8 plus 32 plus 128, 2, and it converges onto infinity. And 10 plus 5 plus 2 multiplied by 1 over 2 plus 1 over 4 would also be an example. Now, normally, if a question asks you what is the sum to infinity of an arithmetic sequence, you can easily know it would be infinity or minus infinity depending on the value of d. If d is bigger than 0, it means it will go to infinity. If d is lower than 0, it will go to minus infinity. But that's not the case for infinite geometric series. Now, infinite geometric series has a special case when the common ratio is lower than 1 or bigger than minus 1. The infinite value actually has a specific value. And you'll be surprised to know why that happens. I'll actually show you as I derive the equation for the infinite series. So this is the equation for infinite series, and I'll show you how we get that. And why we need to have this restriction. If we write the equation for a geometric series, it would be u1 multiplied by 1 minus rn over 1 minus r. Now, the thing is, if r is bigger than 1, because we know we're trying to get s infinity, we get the equation u1 multiplied by 1 minus r infinity over 1 minus r. So we can simply understand that we'll get an infinity number if r is bigger than 1 or lower than minus 1, because the value keeps on increasing and increasing and increasing as it goes. However, think about the case when it's lower than 1 and it's bigger than minus 1. S minus infinity would become u1 minus 1 minus r over 1 minus r infinity. But if you think about it, if I were to multiply 1 over 2, 1 over 2, 1 over 2 again and again and again and again, what would it be? It would be such a small number that we can't even call the value has an actual value. So we can just think of this as 0. Think of it. If it's 0.0000000 dot 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 1, can't we just call it 0? The value is just so tiny that we can just consider this value as 0. So if our value is lower than 1 and bigger than minus 1, actually our infinity becomes 0. So the equation can be written as u1 multiplied by 1 minus 0 over 1 minus r. That is how you derive the formula u1 over 1 minus r, as written in the textbook here. This is the reason why we have to have this restriction and how this equation comes out. So for when the value of r is lower than 1 and is bigger than minus 1, there is a value for infinite geometric series. Now let's look at the note my friend Wani wrote in red. An infinite arithmetic sequence doesn't have a specific value. Yes, I said that before. Because it just converges towards infinity and minus infinity, there is no way you can get a specific value for infinite series of arithmetic series. In the exam, the term sum to infinity usually means the infinite sum of the geometric sequence. Yes, this can inform you that the sum sequence is geometric. So if the question asks you for the sum to infinity, you can automatically expect that the series is geometric series, and you know that the r value is bigger than minus 1 and lower than minus 1. So for some question, they can ask you what value for r does the equation has infinite geometric series, but now you guys will be able to answer that question because I explained the reason why. Let's see. Next we will have scientific notations. So scientific notations involve writing any number as a number between 1 inclusive and 10 multiplied by a power of 10. The result has the form a multiplied 10 to the power of k, where a is lower than 10 and bigger or equal to 1, and k is an integer. Often you may be given values in questions in scientific notation because the value is either too big or too small. Converting between it and regular decimals is confusing since the number of zeros is easy to get wrong just by 1. For converting decimals from scientific notations, for instance, looking at this example, if you have a large number like 9.18 multiplied by 10 to the power of 7, you can switch it by adding the first digit 9, adding the same number of zeros and the power of 10 given 7. And replace the zeros after the first digit with other digits 918000000. Now, I know the way I worded it is very confusing, but if you just look at the steps here, first, just imagine it as 9 multiplied by 10 to the power of 7, so just write 9 in front, and then write 7 zeros. So I would start by writing 9, 1, 2, 3, 4, 5, 6, 7. Because I'm going to assume this number is actually just 9.00 multiplied by 7, 10 to the power of 7. And then now I'm going to start recognizing this 1/8 part and erase one by one the digits and include the numbers that I neglected. So you can see how easily I can just convert scientific notations into big numbers. If you have a small number like 7.16 multiplied by 10 to the power of minus 5, as given in the example here, add the same number of zeros to the left of the digit as the positive of the number given and in the exponents. Then insert the decimal point after the first zero, so 0.00000716. I know, again, this is a little confusing by just saying it words, so I'll just show you by step. First, understand that write 716 and shift it a bit right to the proper notation. So now we're going to add 5 zeros that results in the decimal point. So what I'm going to do is now with this 766, I'm going to write 1, 2, 3, 4, 5 zeros because it's 10 to the power of minus 5. And all I have to do is just simply plot a dot on the second digit and blammo, there's your number that you want to get. So these are the easy way of using converting scientific notations. So you just have to understand and know this method so you don't get confused and don't make a silly mistake by adding a zero or reducing a zero. Now I'll explain how to convert scientific notations to decimals. So first, write out the number just by itself. Now count each number of digits. So 1, 2, 3, 4, 5, 6, 7, 8. Now because we know that digit is 8, minus 1, because we want the first number to be not a decimal. So it would be 7. So you just have to write 9.18 because we want the first value here to be lower than 10, but bigger than 1. So it's 9.18 multiplied by 10 to the power of 7 as a number we have gotten from here. So this is the way you can convert scientific notation into decimals. Then what should we do when it's fraction? Now it's actually the same. You just have to first write down the number by itself. You can just count digits until the largest non-zero number. So it'd be 1, 2, 3, 4, 5, 6. And again, we're going to minus 1 here to avoid confusion between when it's bigger than 0 and when it's less than, to avoid confusion when it's a large number and when it's a number that is really low. So because we now know how much power we're trying to do, we're going to first write the 7.16 because this has to always stay in the region of bigger than 1 and lower than 10. So it'd be 7.16 multiplied by 10 to the power of minus 5. So we also put this question just as a reference. You can also do operations with these since it's all to the powers of 10 and it's easy to rewrite as different powers. For example, if you have the question here of 4 multiplied 10 to the power of 9 plus 8 multiplied by 10 to the power of 9 equals 12 multiplied by 10 to the power of 10, you have to do the last. Oh, my friend made a little mistake here. This is actually power of 9. I'll just fix that for him. And you have to do the last step as the number to the left of the power of 10 can't be less than 1 or bigger than 10. So this number here has now been bigger than 10. So it's outside of the region we want. So we have to convert it again into scientific notation by moving the digit forward and adding 1 to the power of 10. So it becomes 10 to the power of 10 multiplied by 1.2. So this is briefly what I went over with Unit 1. Obviously, I will try to explain all the different rules again when I'm solving the equation. So just make sure to skim through these notes and see if you understand all the concepts. Thank you. This was our first video.